Good afternoon. This is BME 312. This is BME 312. Today we'll be looking at the topic magnetic transducer. Magnetic transducer. In this course previously, we have discussed extensively about various forms of transducers. And we know that a transducer is a device that helps to convert energy from one form to another. It's a device that helps to convert energy from one form to another. So a magnetic transducer is a device that helps to transform mechanical energy into electrical energy, and it utilizes the magnetic phenomena of inductance, reluctance, and eddy currents to indicate the value of the quantity that we are trying to measure. And also, this quantity is in most cases is usually in the form of displacement. This quantity in most cases is usually in the form of displacement. For example, variation in reluctance can lead to a change in the magnetic flux through the coil and also a change in the corresponding electromagnetic force. So when we vary the reluctance, recall that reluctance is opposition to the magnetic field. When we vary the reluctance, it leads to a change in the magnetic force and also the corresponding EMF. The simplest example of a magnetic transducer is the magnetic compass. The simplest example of a magnetic transducer is the magnetic compass. Magnetic field transducers are also known as velocity transducers. Magnetic field transducers are also known as velocity transducers. They are called velocity transducers because the output of the output of the transducer is usually proportional to the particle velocity, which means that as the transducer output increases, the particle velocity also does what? Increases. This type of transducer, usually it consists of a moving coil. It consists of a moving coil in a magnetic field of a permanent magnet. The velocity is usually given as the input, which leads to a movement of the coil in the magnetic field. And this causes an EMF to be generated. So when we give the velocity as input in a magnetic field, EMF is usually generated. So when an electrical conductor moves in a magnetic field, what happens is that it changes the magnetic flux that goes through that conductor. So again, when an electrical conductor moves in a magnetic field, it leads to a change in the magnetic flux that goes through the conductor. And also this produces a voltage. This voltage is proportional to the rate of change of the flux. So V is usually given by N into the phi over the T. Small v, which is the voltage, is equal to N, which is the number of turns, times differ over dt, which is the rate of change of the flux. Similarly, let's look at the induced EMF. The induced EMF is given as minus B times L times V, where B is the magnetic induction, L is the length of the conductor, and V is the velocity of the moving conductor. The velocity of the moving conductor. So the negative sign means that the direction of the induced EMF is usually opposite the direction of the induced current. So B usually has a negative sign. What it simply means is that the direction of the induced EMF is usually opposite to the direction of the induced current. The inverse magnetic effect is also true. When current I passes through the electrical conductor that is placed in the magnetic field, mechanical force F acts on the conductor. So when current passes through the electrical conductor, the magnetic field, mechanical force acts. So when you pass a current through a magnetic flux in a magnetic field, mechanical force acts on it. So F is equal to BIL, where B is the magnetic flux, I is the current, and L is the length of the conductor. Let's look at magnetic sensor principles. There are various magnetic sensor principles in operation, usually in a magnetic transducer. The magnetic sensor principles include the Hall effect, the anisotropic magnetoresistance, the giant magnetoresistance, the magnetic tunnel junctions, and the micro-Hall sensors. There are various magnetic sensor principles in operation. Again, I'm repeating. The magnetic sensor principles in operation are: 1. Hall effect. Hall effect. The second one is anisotropic magnetoresistance. Anisotropic magnetoresistance. Giant magnetoresistance is the third one, while the fourth one is magnetic tunnel junctions. Magnetic tunnel junctions and micro-Hall sensors. And micro-Hall sensors. So magnetic sensors usually operate based on the principle of the Hall effect. The principle of the Hall effect actually has to do with the fact that a magnetic impedance and a magnetic resistance is generated when an electron interacts with the external magnetic field. A magnetic resistance is usually, or impedance is usually generated when an electron interacts with the external magnetic field. In metals, as I said, it's usually electron. The charge carriers are usually electron. So when an electron moves through a magnetic field, it's subject to a sideways force. When you place a small electron in a magnetic field, it's usually subject to sideways force. So, which is F is equal to QVB. F is equal to QVB, where Q is electronic charge, V is the speed of the electron, and B is the magnetic field. You can see the diagram. Let's look at magnetoresistance. Magnetoresistance is the property of magnetic materials that results in a change of resistance with applied magnetic field. Is a property of magnetic materials that leads to a change in resistance when a magnetic field is applied. We have what we call giant magnetoresistance. Usually, it is a large change in the electrical resistance that is induced by the application of a magnetic field to alternating ferromagnets. So when you apply a magnetic field to alternating ferromagnets, usually what happens is that there is a large change in electrical resistance. Let me explain again. When you apply a magnetic field to some ferromagnets, there's usually a large change in electrical resistance. This is what we call giant magnetoresistance. Giant magnetoresistance. We have what we call anisotropic magnetoresistance. Anisotropic magnetoresistance. Anisotropic magnetoresistance occurs in ferromagnets in which the resistivity depends on the angle between the current and magnetization direction. The resistivity depends on the angle between the current and the magnetization direction. This is called anisotropic magnetoresistance. Here are some applications of magnetic transducers or sensors. We can use them in making Hall switches. Hall switches could be used for speed measurement sensors, for magnets in designing laboratory equipment. We can use Hall switches, which is based on the Hall effect. We also have reed switch sensors. They can be used for door alarms, for cleaning rooms in the hospital. Then we have analog Hall effect sensors. We have ferrous metal detection sensors. So we also have other applications of magnetic transducers. We have them in electromagnetic flow meters, in hard sound microphone, in indicating instruments, and pen motor in biomedical recorders. Thank you for your time.